Good morning and welcome everybody. So this is the course on machine learning for the Erasmus Plus program, the Master of Science program at the University of Caen, which is also a collaboration with many other universities from Italy and Spain and France. And what I wanted to give you first is a kind of quick overview of where you find the teaching material. And then we're going to dive into some introductory notes about machine learning, what this course is about. Now, while we move on, feel free to ask questions all the time. Put them in the chat, or if you prefer to unmute yourself and ask questions, please do that. I will try to keep an eye on the chat here and try to answer you as quickly as possible. Now, all the teaching material is available at the GitHub site, which you're seeing now. And for those of you online here, I'm going to put it into the chat so you can access that one immediately in case you have not been able to do that. So in the chat, you will find the GitHub address. Now, what you will encounter, if you're not familiar with Git, by the way, I'm going to say something about that a little bit later here. But this is the main page when you will find the basic introduction, a little bit about the learning outcomes, central parts of the course. The machine learning is actually the where we will have the main emphasis, and a little bit about prerequisites and practicalities. So lectures are typically Mondays from 8 to 10, and we start at 8:15. We try to stay on roughly 45 minutes per lecture, and then we have a small break, stretch legs, grab some coffee or whatever you want to do. And then we begin again at 9:15 and try to finish around 10 a.m. And I hope it's an okay schedule. And then we should also think of organizing a in-person meeting. So I cannot be at Caen because I'm actually in another country. I'm actually in Norway now. And that means that the lectures will mainly be via Zoom. Now, all the lectures will be recorded, which means that you should be able, in case you missed one of the lectures, you should be able to always re-watch the video. Now, the lectures will be uploaded via YouTube, which means that there also will be subtitles. So YouTube normally uses something like almost 10 to 15 hours to generate the subtitles. But the job which is done is actually excellent. And these subtitles can be translated into all the main languages. In total, there are 12 languages, which means that you will have the subtitles in English, but you can easily translate them into French or Italian. You can translate into Arabic or Chinese, if that's your language. So hopefully that kind of service is something which you might find useful. Now, Google uses actually advanced machine learning methods to translate your speech into subtitles, and it takes normally between 10 to 15 hours from when I upload the video till we have the subtitles ready. But I will put up the link as soon as possible after the lectures so you can re-watch the video. Now, the handwritten notes, which I'm also going to present, will also be uploaded right after the lecture. Now, there is also a set of detailed lecture notes which you can access through this link which you see here. And I'm going to put that link into the chat again, so you can have that one as well. So that contains a detailed set of all my lectures on machine learning, and they're being continuously updated. So in case you do a Git pull every week, typically, you will get the latest updates. Then there is also a link to the weekly material. And if you look at that link, you will get into a website which looks like this. And here you can fetch down the teaching material which I will go through on a weekly basis. So today we have these introductory slides, and this is a material which we will cover. We may scratch the surface into session 2, depending on how much time we we have at our disposal today, or how slow or how fast I am today. You will find the teaching material in different formats. You can have a standard one-page format for PDF. There's a plain HTML for searching. There are other types of formats which are typically used during the lectures. And then you have Jupyter notebooks as well. So you should feel free to use this material as your own teaching material. And that means that you can take the notes, the electronic material, and just convert it into your own teaching material. Now, if you now look at the material which we have here, if we now go back to the main GitHub site, so I'm assuming that you have some familiarity with Git, which is a version control software. GitHub is a provider on the same footing as GitLab, Bitbucket. These are all providers which give you access to repositories where you can store your material. I normally always strongly recommend using version control software, and Git is a version control software which is extremely useful and allows you to keep track of what you have done. It acts on text files, and what it does, it keeps it tracks the changes in a text file which you made, so it doesn't save the whole new file after you saved it and committed it to the history of the file. So it keeps only track of changes you made to the text, which means it works best on text files, plain text files, ASCII files. And then you can reconstruct the file which you had at a given moment by running Git, and that will give you the version of the file which you had at that specific day. So suppose you're building a big suite of codes, what could happen then is that you have some errors which you discover, and you don't remember which version was the one which run correctly, but you know that on October the 10th in 2021 you had a version which gave the correct results. And then you can always reconstruct that version and compare it with the present one in order to track changes which you have made. So that's a tool which is extremely useful when it comes to collaborative work. Now, feel free to ask questions in the chat here while we move on, or unmute yourself, as I said. So we are going to cover some basic concepts. We are going to look at statistical concepts. So I know that in many of the bachelor degrees, which many of you have taken, the amount of statistics which is covered has often been a little bit, lacking some of the more fundamental aspects. So we will repeat some of the statistical material which is needed, because the course is also about the data analysis and the statistical analysis of the data. So we will intersperse statistical concepts here and there, and these are quantities like expectation values, variance, covariance, correlation functions. In particular, in traditional machine learning, correlations in the data sets is something which we often are looking after. And then we are going to spend some time on something which I am going to label as low-level machine learning, and that's linear regression and logistic regression. If you can't see my pointer here, please let me know. You should be able to see my pointer here hovering over the text. And linear regression and logistic regression are in principle very deterministic methods. So in the beginning, we are going to see how we can parameterize a function and obtain the parameters by an optimization function. And we are going to obtain the optimal parameters simply by linear algebra and matrix inversion. And the same applies to logistic regression, but here we don't get analytical expressions for the parameters of the model which we have opted for. And then we need to include gradient methods, and that leads to the big topic of optimization of functions. Then we are going to go through some of the classic topics: neural networks and deep learning, convolutional neural networks, recurrent neural networks. And finally, we are going to look at the decision trees, random forests, and so-called ensemble methods like gradient boosting and other methods. So there are many methods here which often based on just plain linear algebra, like linear regression and logistic regression and support vector machines. And then we have other methods where we in principle just let the algorithm learn about the features in the data set which we have. But some of these methods, like linear regression, logistic regression, which I tend to dub as low-level machine learning, they are included in the machine learning family because they contain many of the basic principles which we use again and again in, let's say, deep learning methods. So you can actually read through some of these things here. The thing which I wanted to emphasize a little bit is actually about prerequisites. So we do expect that you have some programming knowledge, and Python has now become the kind of default programming language. You can also write your programs in C++, so Julia is an emerging language, or Fortran. I can assist you with these programming languages as well. But Python has now emerged as a kind of standard for many of these machine learning libraries. And Python contains often wrapper libraries to originally codes which are originally written in C++. We are going to encounter popular libraries like scikit-learn and TensorFlow. So we're going to put an emphasis on TensorFlow, which was released by Google in 2015. Alternatively, if you're more familiar with PyTorch, you can do that. And there are also other libraries. We were going to go through some of these things a little bit later. Now, lectures, since you all are present here now, it's from 8:15 to 10. And we start today. We need to decide when we want to meet. And there will be 2 projects, and each counts 50% of the grade. And we normally plan to have the grades not later than February the 1st. And that's because many of you then are moving to your Master of Thesis places. I mean, we are going to do the Master of Thesis. No, the Master of Science thesis. So hopefully then we should be done by February the 1st. So I put up some tentative deadlines for the first project for December the 15th and the second one for February the 1st. And then after that we will be able to grade things. The teaching schedule, as you can see here, what I'm going to place, I'm going to place some readings, so recommended readings, and every week I'm going to send you an email with some small updates and with reading recommendations. You will find the lecture material here under session 1, and we may sneak into session 2 as well, but that depends on how fast we're moving today. And right after the lectures, I'm going to put up the video and also the handwritten notes. And you can just follow down here. And then when we're getting closer to the end of the year, we may or may not have some sessions in January as well. We did that last year and the year before. And that depends on how far we actually got after November here. So in December, many of you will be busy with exams and other things, so I try not to have too many lectures in December. And we may then probably have some few sessions in January where we wrap up things and discuss the last project. So I actually put up some possibilities that we could meet on January the 14th, but that's something to be decided when we move on during the semester here and just see where we are when we reach the end of November. So I will obviously revise this schedule as we move on. Any questions so far? Practicalities, things which are unclear, or please feel free to put questions in the chat or just unmute yourself and ask questions if you want to. Okay, so as I said, I mean this is the basic GitHub site, and you can see now that there is an icon here with code, and you can click on that one and you can clone the whole material on your laptops or PCs. One thing which I normally recommend is actually to download a graphical user interface, and that's system agnostic. It works on Windows machines, it works on Unix distributions, which you would have on, let's say, on Mac laptops. If you are using Ubuntu or some other Linux distribution, there are actually graphical user interfaces as well, which you can use. And this is actually something which, when you install this, let's say this GitHub desktop, that allows you to install Git as well as a software. So Git is a software. GitHub is just one of the many providers. If you prefer to use GitLab, do that. Or if you use Bitbucket. I should also say that Dropbox is probably something which many of you are familiar with. And Dropbox has actually a version control possibility, but you cannot work on the same file simultaneously. And many of you are also familiar with Overleaf. Overleaf is also a software which allows you to work simultaneously on LaTeX files, where LaTeX is a mathematical typesetting language. Or if you want to, you can just download the zip file. If you want to use these files as your own, you can always fork the repository, as you can see here. And then you can take all the teaching material and just use it as your own. Now, all the material which I'm displaying in these different links here, you will find that material under the doc folder. So if you look into the doc folder, you would then find, let's say for 2022 here, what you could find then are the exercises. You will also find the way we are going to evaluate. So this is a typo here, it should be evaluation and grading. How we are going to evaluate the projects. You will find the different exercises in Jupyter Notebook format. You will find them as a PDF format, and in the PDF format you will also find the LaTeX file if you want to look into that. If you're not too familiar with LaTeX as a mathematical typesetting language, there is also an HTML variant. So this is where you find the source files. Now, if you're not online and you have downloaded the whole repository, if you go to this public or published and you look into, let's say, the introduction here, which is where we are today, and there you will find the material again. So you will find the Jupyter notebooks, you will find the HTML variant or just the PDF variant of the same lecture notes. There's another link which you may find pretty useful, and that's the one on textbooks. So some of the textbooks can be obtained for free. If these are Springer textbooks, so Springer is a publishing house, and they publish, as you know, academic material and textbooks and journals and so on. And if you're an IP number from the university, you can actually download these books for free, and that's a useful thing to do actually. But then I've put in some other textbooks, and there's one textbook which I normally refer to. This book is actually provided for free by the author, the PDF book. So Bishop is a decent textbook. There is also a machine learning textbook, which is more practically oriented with lots of software, and that's the book which I've labeled here as TensorFlow Machine Learning. And that's a scientist which was working with Google before. His name is Aurélien Géron. And that book is, how to say, it's a little bit weaker on the mathematics, but it contains a lot of codes. I've actually borrowed many codes from that textbook. And you should feel free to either buy it or just use this version, which is an older version of the book. There is also the textbook by Hasty et al., Elements of Statistical Analysis, which is this one, which you also can download for free if you are at the university, if you're on a university IP number. So if you're at the University of Caen, you can upload or download this textbook immediately. There is another textbook which is used by many people, which is the textbook by Murphy. This book is good mathematically, but it's a little bit sloppier on codes, so it has much less codes. And then there is an article by Mehta et al., which appeared in Physics Reports, which is an excellent article and gives a very good perspective on machine learning from a physicist's point of view. So let me just take a look at this. There's a question in the chat here. Okay. So guys, I mean, I'm recording the lectures. You can come and go as you want here. So this is very much up to you. And with the recording of the lectures, you can always look back at what we have been discussing. And the recording will be uploaded right after the lectures. So that means that you should be able to actually access the material immediately. So in case you cannot be here at 8:15 to 10, you can always watch the video again at your own pace. So I hope that can be a useful option in case you cannot be there in person or via Zoom actually. Okay, so this link you may find useful. As I said, I mean, this textbook by Aurélien Géron is a hands-on textbook and it's very useful. And then we have the one by Hasty et al., which is a kind of standard reference in machine learning or statistical analysis of machine learning methods. And we also have the one by Bishop here. And finally, there is one textbook, if you scroll down on the README file, if you go to the end here, there's a textbook which I am pretty fond of and which covers quite well many of the deep learning methods. And that's a textbook by Goodfellow, Benjo, and Coville. And you can access every chapter here. And we will essentially go through chapters 1 to 12. In this, what they have done, they don't give you the PDF or the full text, but they give you the PDF of every single chapter. And this is a book which, on a weekly basis, I'm going to send you reading recommendations from this book. I will also send you some reading recommendations from this book, which you can access for free if you are at a university, if you log in with a university IP number. And you also have the book by Aurélien Géron. So these are the books which you will receive links to on a weekly basis with some kind of reading recommendations. Okay. There are also some other textbooks here which you can look at. I mentioned the book by Murphy, which is a pretty good book. And also during the lectures, the weekly material, I'm going to send you links to useful videos which illustrate some of the topics which we're going to cover. Finally, the other link which you can look into is actually the one with a full set of lecture notes. And this is actually based on a course which I teach at the University of Oslo. And the teaching schedule there is not that different from the one which we are following. But here you will find the different chapters, as you can see. And this is the full Jupyter book with all the teaching material. And it's also something which allows you to search through all the material here. So it's a useful feature with Jupyter notebooks and Jupyter books. Normally you cannot run the files here, because if this is actually produces just the output from the program, which you will see in the text here. But we are going often during the lectures to run Jupyter notebooks. Okay, any questions so far? Is everything clear? You can, in order to get started and find the material, you can always revisit this video here. There is also a video down in the README file here to a link on how to use Git and GitHub. So what I'm going to do now is to jump into the weekly material, and we are going to try to get started with machine learning here. So let me just bring this up, and let's look at some of the basic elements on machine learning here. And I'm going to skip, I'm not going to say everything here, but the topics which we will cover are linear regression, logistic regression, or what I dubbed as low-level machine learning methods. And then we are accompanying these analyses. We are going to look at the statistical analysis, and we are going to see how we can optimize the problems. Then we are going to look at decision trees, random forests, and other methods, neural networks, deep learning methods like convolutional neural networks and recurrent neural networks, and also how to analyze experimental data. And ideally, machine learning represents the science of giving computers the ability to learn without being explicitly programmed. You will see now that when we deal with what I call low-level machine learning methods like linear regression and logistic regression, these are actually very deterministic methods. It's at the end, you end up just inverting matrices. But the idea is that you have a generic algorithm which then can be used to find patterns in a broad class of data sets. What you should keep in mind, and we are going to stay within the machine learning subfield of artificial intelligence, and we are basically going to look at algorithms which are developed by humans. So it means that we will have well-designed algorithms which will allow us to study a specific data set and try to find correlations among the features in the data, and also try to make predictions. So traditional machine learning is about making predictions and finding correlations in the data sets. So you should also keep in mind that the kind of insights and knowledge you have about a specific system, they do play a central role when you develop a specific machine learning algorithm. So it's an extremely rich field. It's a pretty new field. What makes it exciting is that there are still many things which are not fully understood. So a discipline or sub-discipline like the mathematics of deep learning methods is a field which is under development. There are popular libraries which are written in Python or contain Python wrappers to C++, so Fortran codes. And these typical examples of libraries are scikit-learn, which we are going to use quite a lot. So scikit-learn provides also a lot of, what should we call it, something like codes which can be, or functions which can then be used together with other libraries like TensorFlow, which was released by Google in 2015, PyTorch, which was released by Facebook almost at the same time, and Keras, which is an API to TensorFlow and makes life much easier when we are using TensorFlow with deep learning methods. And they're all freely available at their respective GitHub sites. And if you take a look at the number of developers, I mean, you will see that there are thousands of people adding to the functionality of these libraries. So it's a very fluid field. There are tons of new ideas being proposed almost on a daily basis. And it's a rich field in spite of its young age, and it's a very exciting field because it's a field which is being moved by young people. And there's a lot of creativity and lots of new ideas. And not all of them are founded in kind of mathematical rigor, which makes it a little bit exciting because you can also play around and see if it works or not. And then you can ask yourself, why is this functioning and why is this not functioning? So there are tons of things which can be done. And for us physicists, there is a lot of material to explore and to apply to physics problems, like the classification of events in nuclear physics experiments, because in many experiments now you're going to produce terabytes of data. If you think of an experiment running at CERN, typically every second when you run at the LHC, you produce from terabytes to petabytes of data. And these data are normally compressed down to gigabytes, and an experiment can run for half a year. And then you can do the math yourself and find out how many seconds and how many bytes of information you will actually have. Then, clearly, this is something which needs to be automatized. You need to think of smart ways of representing your data. And if you want to search for specific events, there's no way a human can go through petabytes of data in order to find a specific decay process. The same thing happens in nuclear physics. You will see many cases now where you're producing data in the terabyte region, perhaps even in the petabyte region. And that means that you need to automatize some of the searches for the events. And then when you have classified some of them to belong to this and this type of events, you can then run your traditional algorithms and do the standard data analysis which people have used from the early ages of experimental nuclear physics. It's a multidisciplinary approach. You need to have a pretty good understanding of linear algebra. So linear algebra actually plays an essential role. You will see that many of these algorithms, when we are implementing them, they are being reduced to efficient handling of matrices and vectors. Many of them involve linear algebra algorithms. There's a lot of statistics, understanding errors, Monte Carlo methods play a central role, and so on. So this makes the field exciting because you need to bring up the knowledge or bring back the knowledge which you got when you went through courses in mathematics and statistics, and then obviously you have to tailor the application of these methods to the specific physics case. Now I've put up something about learning outcomes, but I will leave that as a kind of reading material to you guys, so you can just take a look at these things. We are going to run this course in a project-based way. So the assessment which we're going to make is through projects. So there is no kind of written oral exam. It's actually you collaborating on projects. And you can team up with groups. The optimal groups are typical 2 to 3 people. But every year we also had groups of 3 to 5 people. As long as you can collaborate well together and you're feeling comfortable with each other. I mean, you can also have groups of up to 5 people. But during every time we've run this course, most people have actually ended up forming groups of 2 to 3 people. But this is very much up to you. So the working on the experiment or the numerical example is actually an important part of the course here. Now, I wanted to say a little bit about the types of machine learning which we are going to put emphasis on. So we will mostly look at what's normally called supervised learning. So that means that your data are labeled. So you will have input data and you have output data. And both the input data and the outputs have been labeled. And then what you're going to do then, based on the input, is to try to make a model which can make predictions about the output. This is essentially what many of these machine learning methods deal with. Then we have unsupervised learning, which I mentioned a little bit earlier, and we will discuss some of these things through what's called principal component analysis and clustering, and that's a method for finding patterns and relationship in data sets without any prior knowledge of the system. We are not going to touch reinforcement learning, but we will stay mainly with supervised learning. So if you think of deep learning methods like neural networks, recurrent neural networks, or convolutional neural networks, which are highly used in imaging, then these are methods which are very data greedy, and they are based on you having labeled data in order to train a specific model. And then we are going to deal with some major types of problems. So one is classification. In classification, you have a typical output which is discrete. It could be a binary one, like a true, false, yes, no, sick, not sick, a tumor which is benign or not benign. So this would be an example of a binary case, but you can have more classes. One example which is very much used in machine learning is the example with handwritten numbers from 0 to 9, where you train a model to actually recognize handwritten numbers, and these are data sets which then have 10 classes, the 10 numbers from 0 to 9, just to give you another example. And then we have the other case, which is regression, where you assume that your data is represented by a function, a continuous function, and then you want to fit that function. So that means that the goal is to construct a function that maps input data to a continuous output value. So you assume that behind your data there is a function f of x, which ideally should represent the data set. We are coming back to this. Then we have clustering, and data then typically divided into groups with certain common traits and without knowing the groups beforehand. This is a form for unsupervised learning, and it's very much used in trying to classify events from, let's say, nuclear physics experiments. So, irrespective of what we do, we have three basic elements in common. And whether irrespective of whether we are dealing with supervised or unsupervised learning. So the first ingredient is a data set. And that can be subdivided into training and test data. We are coming back to that. Just to mention that the training data is what's used to train a model. And the test data is then left out of the training. You can think of keeping the test data in a vault. And then when you have trained the model, you have validated the model and found the best parameters which give the best reproduction of the training data. Then you would apply it to data which have not been included in the model. And this would be the test data. And many find actually the most difficult part of using machine learning to be the setup of your data in a meaningful way. In this course, we will, in most cases, have data sets which are almost ready-made. So that means that this part of setting up the data is something which we are not going to focus that much on. We will mention it, but we will often have either some simple cases where we produce the data again and again, or we are going to use libraries like scikit-learn, or you can go to websites like kaggle.com, and there you will often find data which are almost ready to be used with many of these machine learning algorithms. Then the second part is you making a model. And this is normally a function of some parameters. And the model normally should reflect the knowledge you have of the system. If you think that the model is well fit by a polynomial, then you will try to decide the parameters of the polynomials. These parameters are often also called the estimators of the model. So we are going to mix the word parameters and estimators interchangeably when we move on with the different lectures here. So the next part is to have a function which you use to assess the quality of the model. And when you have these three ingredients, then what you can do then is to try to optimize your model with respect to the function you have decided to assess the quality of the model. So I want to give you an example now of these three ingredients. And so what I'm going to do now, before we take a small break, I'm going to set up the basics for what is called linear regression or ordinary least squares, so that we can actually illustrate what these three elements actually mean. So if you move on a little bit, at the heart of all these methods, what you have is an optimization of the function you have chosen to assess whether your model is a good one or not. And these leads normally to, unless you can find analytical solutions for the unknown parameters, you will often have to solve the equations numerically. And that brings us into the field of optimization algorithms. And one of the standard methods is actually the gradient descent method, which is the simplest possible one. So let's now break down this monotony of me just reading from the slides here and try to bring forth a simple example where we are going to look at what these three ingredients mean and what they can represent and how we can deal with them and find perhaps even an analytical solution for the parameters which we want to use to make our model here. So let me stop sharing and then we move over to the whiteboard. So if we now, before we take a small break, if we now look at what we said, so, and we are going to link this up with linear regression. And the first method which we are going to meet is what you have met before in linear algebra courses, and that's normally called ordinary least squares, or just the least squares method. So I'm going to use an acronym OLS for that. So what we are going to assume now is that we have a domain of input and output data. And let's just call this domain for a D. And that contains a set of data observations. So we have X, which is the input, and then we have an output. So we would normally call this an input, and we call this the output. And then we have a set of measurements, or this can be the result of a heavy calculation, and then up to x of n minus 1 to y of n minus 1. So this is the domain of data, and that was the first element in machine learning. The next thing we are doing now is to make a model. So the basic assumption in linear regression is the following. So when you don't see, by the way, when you don't see subscripts on the different variables, then I'm assuming that these are vectors. So we are now assuming that there exists a function of x. So this function f of x is a continuous function. We don't know that function. But in linear regression and in many of these regression methods, we are simply assuming that there exists such a function. We don't know that function, because if we knew that function, I wouldn't be preaching to you now. Then there is an additional term which is assumed to be a normal distributed noise. So this epsilon is a normal distributed noise. That's an assumption which is made in the derivation of the equations for linear regression. So this is normally distributed noise. So what we are assuming is that this epsilon is now given by a normal distribution. So you will see this symbol n, which refers to a normal distribution with zero mean value and a standard deviation or variance in our case, which is given by sigma squared, where we haven't defined what this variance is when it comes to its numerical value. But the mean value is set to 0. Okay, so this is the assumption which is made. Now we don't know this function. So we simply assume that there is a continuous function. So what we make then is a model. So we make a model where we now assume that this function f of x can be approximated by a model which we make, and I'm going to put a tilde on top of y to indicate that this is now a model. So when you see this symbol with a y tilde, this is the model which we have made. We don't know whether this is a good reproduction or not, but we have made a model. So that means that what we end up with is that y of x is now going to be approximated with this y tilde of x plus this normally distributed noise. So this is the basic assumption. So that means that we are going to have a functional dependence, and I'm going to write this as a y of I, and that's going to be written as a y of I tilde plus some epsilon I. And normally we assume that this epsilon I is the same for all the inputs and outputs here. this is the model which we have made. We haven't yet decided what the model is going to look like, but you could think of the model as a polynomial. In X. So that means that we could now make a model y tilde of x of I, which is over y I tilde, which is now a function of a polynomial of a specific degree. So we could start with j equal to 0, and we could obviously include all points if we want to, or we could just go up to a polynomial of a specific degree. So what I'm going to do now is to take away n, which is all the data set, and rather put a p here. So p is now the number of polynomials which we have, or the number of features, or the number of parameters if you want to. And we are going to have a beta j multiplied with x of I to the power of j. So that means we have a polynomial of beta 0, which is the intercept, if we have a polynomial fit. Keep in mind that we are not limited to have a polynomial fit. So this will then obviously have beta 1 times xi to the power of 1. There's going to be a beta 2 for the second order term, xi to the power of 2. And this goes all the way to the last parameter. So remember now that if we have 2 points, we can fit a straight line, first order polynomial. If we have 3 points, we can fit a second order polynomial, 4 points, a third order, and so on. And we are assuming that this p is not necessarily equal to the number of data points which we have. And this would then be given by x of I of p minus 1. So, and we have assumed that this p, which we are going to call the number of features or the number of parameters, is less or equal than the number of data points which we have. So that's the model. And then the last point is actually to assess how good the model is, or assess the model. So we need to find functions which we use now to assess the quality of the model. And this is where you guys now deserve a break. But if we now have a polynomial fit and you want to assess the quality of the model, there is a famous function which many of you have met before. So I'm just going to leave that as an open question to you. What kind of function can you think of in order to assess the quality of the model which we have? So I just leave that as a question. Feel free to answer in the chat. So we want to find a function which we are going to call the cost function, which is a function of beta. So this is normally called the cost or the loss function. In other fields, it's called the error function. If you go to finance, it's called the risk function. But this is a function which we now define in order to assess the quality of the model. And when you do linear regression and fitting a polynomial, for instance, there is a famous function which is often used to assess how well you describe the data. So feel free to think of that during the break. I'm going to pause the recording now during the break. Welcome back to the second session today. There's a question in the chat here about the projects and whether they can be partly defined by you or fully defined by you. So the standard recipe is that I will present a framework. So typically for project 1, we are going to deal with linear regression and logistic regression. But then the data sets, if the data sets which I propose are not that interesting, and you have some other data sets you would like to analyze, this is something which is fully possible. So I want you guys, to feel this kind of flexibility in defining the type of problems. So if you have a research problem which goes in these directions, using some of the algorithms we are going to discuss, feel free to propose alternative projects. And if somebody wants to collaborate with you on the data sets, and this is something which we have actually done every year. There's somebody who may already have some data sets they want to analyze for their master thesis or for some specific project they're interested in, for some research topic which you are connected with, then feel free to team up. So I would like you guys, to if you want to, we can set up a Slack channel where people can set up ideas. So if there's an interest in that, I can actually set up a Slack channel a little bit later, and there we can just drop ideas. And if people want to team up with somebody on some data sets, even better. And then you can collaborate. So collaboration is something which we normally encourage here, because being together 2 and 3 people or even more is extremely beneficial for all of us. I mean, some of you may be pretty savvy on mathematics, some of you may be very good at programming, and some of you may be just like me, who's good at making coffee and then crack all kinds of lame jokes. So you need that kind of people also in a project, maybe. Okay, the other thing which I wanted quickly to mention is a time for a meeting in person. So one possibility which I see is some weekend in the beginning of November, which could be a possibility that we set aside, let's say, a Saturday and a Sunday, and perhaps also parts of Monday morning when we can have these lectures, and just meet in person and discuss more in-depth exercises and projects and so on. And I would say that in the beginning of November is a timing which could fit well, the first half of November. But I want you to think a little bit about it, whether this is something which you find useful or not. Okay. So again, let me put that in the chat here. So one thing, if you're interested in a Slack channel for communication, and I'm going to send an email with a Slack channel here, and then also time for, and this is something we can always set up when we have a Slack channel for communication, and time for in-person meeting. And I would say this is first half of November. So you will find that in the Slack channel, in the chat here. Now, what I wanted to do now is to go back to the simple cases which we are setting up now, which are going to lead to the standard equations for ordinary least squares. So I said before the break that there is a famous mathematical function which is used to assess the quality of the model. So any ideas, suggestions from you folks about what kind of function could we define in order to assess whether this model which we have defined, so what we have is a model which gives us y of I, and we want to compare that one with the data which we have to be compared with the output. So we have an input x, and then we want to compare to be compared with y of I. So there is an answer in the chat here, and let's see. So that's the standard deviation is one of them, but the mean squared error is actually one of them which is most used. Another one which is very much used is actually the relative error. So let's bring up these definitions here, which are, so the standard deviation is one way to assess it, and the standard deviation is close to the mean squared error. But let's look at the mean squared error. So I'm just going to write that as an MSE, and this is going to define the function which you will normally find named the cost or the loss function. If you go to finance, you will see this is called the risk function. I often like to call it the error function. But we are going to define that one to be 1 over n, the data set. So this is actually a sample average. And we can later translate that one into an expectation value. So we run over all the data points. And the reason why I start my counting from 0 is that arrays in Python, they start with the 0th element first. So the first element is number 0. So the mean squared error is actually y of I minus y of I tilde squared. So this is actually one of the most standard functions which is actually used to assess the quality of your model. And this is a function which actually puts emphasis on outliers. So outliers are typically values which deviate a lot from what your model would predict. So if you have a large deviation, that would typically actually emphasize that value. Another type of error function could be the absolute value or the relative error. So let's just set up the relative error. And the relative error is normally written as a absolute value of y of I minus y of I tilde divided by the absolute value of y of I. Now here we have to be a little bit careful because we don't want to divide by 0. So we have to look at cases where y of I is not equal to 0. So this is one possibility. You will find these quantities in a more compact vector matrix representation. So we are going to define a vector y, which now contains all the y's, y0, y1, down to yn minus 1. So this is going to be a vector of length n. And the same applies to y of I tilde. So we don't need to set up y of I tilde, hopefully not. So that means that I can actually rewrite the mean squared error as a 1 over n. And I don't know if you're fully familiar with this kind of notation of the norm of a vector. So I have a vector y minus the vector y tilde, and this is norm 2, and this is squared. So the norm of a vector and the norm 2 of a vector, so if you see a vector x, norm 2 here, that's actually a sum over all the elements, and then we have the elements x of I squared, but we are taking the square root of this quantity here. So it's actually the square root. So when you see it squared, it means it's actually x of I squared. So this is the norm 2. So when you see something like x2 squared, this is simply just the sum over I of xi squared. So the mean squared error is actually a function which is used repeatedly. Now, if you look at the mean squared error, the thing now is that what we are going to make now, if we make a polynomial fit of this y of I, what we have is a sum over j equals 0 up to p minus 1, and then we have a beta of j, and then we have an x of I to the power of j. So in total what we would have then is a set of unknown parameters, and I just write this as a beta. So I would have a beta 0, which is the intercept, a beta 1 down to a beta p minus 1. And this is a vector with unknown parameters of length p. So p can actually be equal to n here. Now what does that mean? If we now try to rewrite this in a slightly more compact way, so let's try to look at y0, the first element. So this is now going to be, or y0 tilde is actually going to be equal to beta 0. If I now use this polynomial approximation, and it's going to contain beta 1 multiplied with x0 plus beta 2 multiplied with x0 squared, and then we move all the way up to beta of p minus 1 x0 to the power of p minus 1. Then we have y1 tilde beta 0 beta 1 x of I x1 sorry plus beta 2 x1 squared, and all the way again up to beta of p minus 1 of x1 of p minus 1. And then we move down all the way to y of n minus 1, which is equal to beta 0 plus beta 1 xn minus 1, and I'm just writing plus plus here. Now if you look at this equation here, how can we rewrite this in a more compact form? Because now what you have on the left hand side, so the left hand side you have a vector, which is y tilde. On the right-hand side, you also have a vector of beta, but then the x's could now be represented as a matrix. Excellent. So we can actually rewrite this in a compact form where we have a y tilde is equal to a matrix X times beta. And this X has a name in the literature which is called the design matrix. You will also find this as a feature matrix. You will also hear it being labeled the predictor matrix, and so on and so on. So this matrix, now keep in mind that you have a matrix which is based on a polynomial. This is the approximation you have made about the function. So this x is now obviously the intercept, has to be equal to 1, 1, 1, all the way down to 1 here. Here I have x0, x1, x2, down to xn minus 1 to the power of 1. Next I have x0 to the power of 2, x1 to the power of 2, and this goes all the way down to xn minus 1 to the power of 2. And this continues till the last element, which is x0 to the power of p minus 1. So remember again that p does not need to be equal to n. And this is p minus 1. So note now that every column here represents a feature. So the feature represents now the polynomial degree which we have. This does not need to be a polynomial, as we said. It could be a sine function, it could be another type of function which is more appropriate for the type of problem which you have, or it could be a data for a classification problem. So suppose you want to classify whether a set of tumors is a benign tumor or not, and then this will be characterized according to the features of the tumor. So the tumor could have a feature like its perimeter, its thickness, its radius, its color, and so on. And these will be things which you would encode in each column. So I'm going to use a notation now where this X is going to be a matrix where n is the number of data entries which we have, times p, where p is a number of features. So this is the way I'm going to organize my data set now. So n is the number of features. No, sorry, n is the number of data points. Number of entries, data entries. So you could have something like 1,000 patients, and then you could have something like 30 features, which then classify whether this is a benign or not benign tumor. So, and this is the number of features. In our case, in this kind of vanilla example, the number of features is actually something which represents the polynomial degree. So the columns, in the notation which I'm going to use, represent the features, and the rows represent the data entries. And I'm going to stick with this kind of notation here. So that means that my y of I tilde is now given by a sum over j equals 0 up to p minus 1 of xij, where xij is a given matrix element of the design matrix, multiplied with beta of j. And sometimes I'm going to represent this in a kind of more compact way. I'm going to write an I here and then an asterisk to indicate that I'm simply taking a given row and I'm multiplying all the elements there with the relevant column numbers. So these are just notations which I'm going to introduce here. Now, when we now introduce this in our function, the mean squared error, so we are going to have a C of beta. This is the cost function, which is the mean squared error, which is now given by this sum over j equals 0. Now I equals 0. Up to n minus 1. And we are now going to have a y of I, this is our data, minus the model y of I tilde squared. And this is now given by 1 over n of I equals 0 of n minus 1. And then we have a y of I minus, and we have this sum over j equals 0 to p minus 1. And then we have a xij of beta j squared. So this is the mean squared error. Now, we could now make a simple model. So we could now assume that this y of I tilde is simply given by beta 0 plus beta 1 times x of I. So we have a first order polynomial. Now, another thing I wanted to emphasize to you, when you look at what we did here, so this specific notation which we put up, the way we have set it here, what you note now is that y tilde is a model which is linear in beta, and that's why it's called linear regression. The model I can make with the x's doesn't need to be a linear function. This could be a polynomial of degree p, or it could be any other function which I think or you think is the best way to represent the data. So keep that in mind. So note now that, so I want to encircle that one. So let's just do that. So it's linear in the unknown parameters beta. And that's why it's called linear regression. It's not called linear regression because I am making a model down here which is linear. So this is my polynomial fit. So this is linear in x. But that's not what gives the name to the method, which is linear regression. It's linear in the unknown parameters beta. So this is linear polynomial. And that means the matrix, in that case, the matrix X is going to be a matrix of dimensionality n times 2. So that's a much smaller matrix. And often what you will see, the normal case, is that the number of features which we have is that p is normally smaller than n, but often it's much smaller. P is much smaller than n. Now, what I'm going to do now is to give you the result when we take the derivatives. So the optimization now, the whole optimization process, so the mean squared error is one way to assess the quality of the model, as we said. Now, there's another thing which another function which I could have used, as we mentioned. I could have used this function, the relative error. Or I could say, no, I prefer this one. So the mean squared error puts an emphasis on the outliers. Now, if you look at the mathematical form here, because what we want now, so let's go down a little bit. So what we are going to do now, and I'm going to write this in terms of all the parameters, dc beta 0, and we want this dc of d beta 1, and this is all the way up to dc of d beta of p minus 1. We want these to be 0. So what we are going to have is a function which now depends on the vector beta. So I'm going to write this later in a matrix vector notation, and I want this to be 0. So when you now take the derivatives, if you look a little bit at what we have here, to calculate the derivative with respect to the betas here is actually pretty easy. And you're going to get a continuous function. If you look at the relative error, on the other hand, what happens if you take the derivative now with respect to your parameters beta? So we have still, when we do this here, we are still making this assumption that y of I tilde is given by this xi star multiplied with beta. So we have kept a linear model in beta. So what kind of problems do you see when you take the derivative of an absolute value? So any good suggestions? Feel free to unmute yourself. So let me give you a small hint here. So what kind of cost function you choose is something which depends on, it's a discontinuity. X, it's not smooth everywhere. So you know, if you take d of x of dx, this is equal to plus 1 when x is larger than 0. It's minus 1 when x is less than 0. And it's undefined, as far as I remember, if I go back to my courses in basic mathematics, and it's undefined for 0. So normally what people do, most practitioners, when they deal with these kind of derivatives, you often put that to 0 when x is equal to 0. But formally it's not defined. So this gives some small complications. So what I'm going to do now, before we go back to the slides, I want to give you the answer. So when I take the derivative of dc d beta of our cost function, which is now given by this function which we have here, the mean squared errors, which I wrote like this, but you can also write the mean squared error, and I leave that as a kind of small exercise till we meet again next week, because then we're going to look a little bit more at the mathematics. Now I wanted to give you some kind of more overarching view of things. So when you do that, what we have to do is to take the derivative of d beta, and this is the derivative of 1 over n, and we can rewrite this in terms of y minus x, the matrix, the design matrix, transpose, and this is multiplied with y minus x times beta. So I should write a small x here, just to indicate that that's multiplied with. So this is the quantity whose derivative we want to take when we now rewrite the mean squared error in terms of vectors and matrices. So this is nothing but a rewrite. And remember now that the mean squared error, which we calculate, this c of beta, is a scalar. So that means that we have to produce a scalar when we calculate these vectors and matrices multiplied with each other. And that's why we have the transpose multiplied with y minus x times beta. So I'm going to give you the result now. So what we have is a dc of d of beta. In this case, when it's 0, it's going to be given by minus 2 divided by n. And we are going to have an x transpose of y minus x times beta. And we want that to be 0. And that means that x transpose times y is equal to x transpose times x times beta. And then we find the optimal value. So a beta hat is now the optimal value. And we are going to have an analytical expression for this unknown parameter, or feature as we called it, or estimator as you will often find it in the literature, of xt times y. This is the expression which we will derive next week. And this expression which you see here is an analytical expression. And if you can invert that matrix, then there is no problem at all. Later we will see how we can circumvent the case when the matrix is not invertible, because that can happen. So if the matrix X has dependencies between the different columns, you cannot invert that matrix. But now I'm just stating the result here. And then next week we are going to go through the details of how to derive that. But I wanted to give you this kind of more overarching view today. So what we have is that beta, in principle, is the minimum. So it's the argument minimization here of beta element in R of length p. And then we have a function c of beta. this is the final step, which is the optimization part. So we said that we had the data, part 1. 2, we make a model. In our case, we made a polynomial. It doesn't need to be a polynomial. But what enters the setup of the design matrix reflects obviously the way we design the problem. When we have that, we need to assess whether this is a good model or not. In many cases, we would like to have a function which has a continuous derivative, a smooth one, which we then can handle easily, numerically or analytically. And then what we need to do next is the final step, and that is step number 4, which is the optimization. And for linear regression, when the function depends on the unknown parameters beta in a linear way, we end up with a simple analytical expression if we start with a mean squared error and we simply have a linear dependence on the parameter beta. So this is the simplest machine learning method we can think of. And you would ask yourself, why is this called machine learning? Because this is something which we saw in the basic linear algebra course when we started at the university. Now, it is included in the machine learning family because we can actually derive the same equation from a statistical point of view. If you assume that the variable y's are distributed according to a normal distribution, you can actually derive the same equation. And that gives you a basis for interpreting things in a simpler way because we have analytical expressions for many of the quantities. And we can then build up an intuition about the basics of machine learning methods. And that's why linear regression, although it doesn't sound like us letting the algorithm find out the optimal parameters by a kind of non-human way of doing it, it sounds like an kind of exaggeration. It is an exaggeration because in most cases we end up writing explicit algorithms. But it's included in the machine learning family due to its pedagogical features. So we are going to build up our intuition about machine learning methods, starting with these simpler methods. And that allows us also to bring in many other concepts. So what I'm going to do now is to go back to the slides and say a little bit about some of the technicalities and things which we need to look at. So let me just go back to the slides here. And please feel free to ask questions if something is unclear. So in the slides, you will find these elements, which we now have been discussing, the first ingredients. And then at the end, what we end up is an optimization problem. And in this case, with linear regression, we have analytical expressions for standard ordinary least squares. But normally what we need to do is to calculate gradients. And that leads to the whole family of gradient methods. And that's the optimization problem is one of the big issues in machine learning algorithms. And making progress there can have huge impact on many central machine learning methods. And just a little bit jokingly, if you want to get many friends, that does not mean that you guys don't have friends. If you can come up with efficient methods for calculating gradients, you will get many friends. There is, for instance, an algorithm which is called the Adam algorithm, which we are going to meet, which has more than 100,000 citations. And that says a little bit about the popularity of gradient methods. And if you can make progress there, that's going to be central for many machine learning algorithms. Now, in the slides here, what you will find is some discussions about frequentist and Bayesian approach. So traditional machine learning has more been about making prediction and estimations. You are less interested in a probability distribution, but we physicists, we are interested in both making predictions. We are interested in being able to estimate the errors of the parameters. So in linear regression, you can actually estimate the errors. You have an analytical expression for that from ordinary least squares. But in most other cases, you need to find the probability distributions. And with a probability distribution, you can deal with causations. You can say A leads to B, but B does not necessarily give you A. So this is something which I want you to look at. Just take a look at these things. It's something which I feel this kind of split between a frequentist approach and a Bayesian approach is something which I find a little bit artificial. But in statistics, actually communities which almost fight each other over which approach is the best one. But in machine learning, in traditional machine learning, we typically use a so-called frequentist approach where the aim is to make predictions and find correlations. And you focus less on, for example, extracting a probability distribution. So there are some things about a good model, but I'm going to skip that. Now there's a lot of practicalities. So what I would recommend is that we use Python. And I hope that many of you are familiar with Python. You can code in C++ or Julia if you want to. Julia has great support for machine learning. You can also use R if you come from more a statistical point of view. In statistics, R is often used, but Python is taking more and more over. So I am pretty, I'm very agnostic. I like to use the best method and what makes life easier. And I think that Python now has really emerged as a very good programming language for machine learning methods. And it contains, like if you look at scikit-learn here, that's a very popular library. So there's something about installations. Normally what I recommend, if you are not too into setting up dependencies and paths and so on, many people use Anaconda, which is an integrated kind of development environment, and it sets up all Python dependencies and so on. But you should obviously feel free to set up things yourself as you want. If you don't want to use Anaconda, you can use a minimalistic version of Conda, which installs many of the packages for you and sets up the dependencies. Anaconda normally installs tons of files, and sometimes when you want to uninstall it, it's not clear whether it uninstalls everything which was placed there. Google's Colab is excellent. Feel free to use that. That's a free Jupyter notebook environment. No setup and runs entirely in the cloud. It allows you to access GPUs and CPUs from Google. So that's something which is worth looking at. You have libraries here, and in the notes for this week you will find examples on how to actually use these libraries. So there is NumPy, which is the basics for dealing with arrays and matrices. There's Pandas, which I normally recommend using. There is also a library called XArray, which is a Python package for working with more than just two-dimensional arrays. So if you're dealing with tensors, XArray is actually an extension of to NumPy. SciPy, Python-based ecosystem, open source software for mathematics, science, and engineering. I guess many of you are familiar with Matplotlib. And then Autograd, and now recently JAX, J-A-X, allows you to calculate derivatives of your cost function, for instance, to numerical precision. It uses the chain rule in a repeated way. And I normally strongly encourage you to use Autograd, automatic differentiation. It's a fantastic algorithm. Symbolic Python, symbolic mathematics. And then we have these libraries like scikit-learn, which has a functionality which integrates with TensorFlow, PyTorch, Theano, and Keras. So many of the functionalities we are going to look at, like splitting our data in test and train data, and many other things, they follow with scikit-learn, and they can be used as a way to input data to, let's say, TensorFlow or other machine learning libraries. So scikit-learn is a kind of basic library we are going to start with. So I recommend having these installed. If you're using Anaconda, I think now scikit-learn comes automatically, and I think also TensorFlow comes automatically. So in the slides you will find, if we now switch to the Jupyter Notebook. So this is a Jupyter Notebook for today. You will find a lot about NumPy, I invite you to take a look at this. If you're a little bit rusty on how to use NumPy, the library which I wanted to introduce to you is actually the library called Pandas. So in NumPy you also have statistics functions like calculating the mean of a function. You can calculate the covariance of a matrix. You can calculate the standard deviation easily, and so on. But there's a package which is very useful, which we are going to look at again and again in order to organize our data. You can also do mathematics with Pandas. So Pandas is actually it stands for panel data, and it was originally developed for econometrics. But it's an efficient library for data analysis with an emphasis on tabular data. It has a lot of functionality which allows you to read easily from file. So here you can make your own data and you can display it. So you can now see what kind of movies and books I was hooked on. So you can then have an index here, first name, last name, place of birth, date of birth. You can make a list of employees of a company. And then what it gives, so with the data frame here, which is one of the options when you're dealing with matrices. So you would simply import pandas as PD, and then you would write PD data frame, and this defines an object now which I can display. I can do mathematics with this object if I want to, if I were to transform the entries here, the characters, into numerics. And then you can add functionality here. You can change the index, so that instead of having the default 0, 1, 2, 3, you can then change the index to something which is more relevant. This would be a nickname or first name or whatever. You can display it easily. You can display one of the entries, and that gives you all the types of entries you have for that specific entry. And then it also tells you what kind of object it is. You can easily add data to it, and so on. You can do mathematics with it. So like here, you can define a matrix of dimensionality 10 times 5. And in this case now you set up a matrix with random numbers given by the normal distribution, like here. And then you can define this object, DOF, which is now given by this data frame functionality of Pandas. I can display it, which I've done here. So this is now my 10 times 5 matrix. I can calculate the mean value of each column. So this would be the mean value of each column. So I take all the column elements and calculate the mean value. This is something you will encounter when we are normalizing the data in machine learning. So this is a very useful feature. And you can calculate the standard deviation. You can do mathematics. You can square each element, df squared. So these are the squares of the elements, as you can quickly see by just squaring these different elements. You can do much more. You can make plots of the data. You can find the mean value, the standard deviation for each column, minimum, 25 first percent, 50 first percent, the max value of each column, and so on. And you can make plots here of these quantities. You can produce a 4x4 matrix if you want to, and then many operations here. So one of the things I wanted you to take a look for to next time, when we meet again next Monday, is to go through some of these examples here in the slides. There is a simple example here on how you use scikit-learn and linear regression. And in this case, there is a simple data set where we take a data which is given by a first-order polynomial plus some normal distributed noise. And here I'm just using scikit-learn to make a prediction. And you can play around with noise or not noise. So if I take away the noise and you run this case, you would then see that you get an almost perfect fit to the data. So the data are the circles here. I also want you to take a look at the first nuclear physics case, and then we're going to start looking at that next week. So take a look at these examples, And then the first nuclear physics case which we have is an example where you're going to fit the nuclear binding energies, or the nuclear masses, to the so-called liquid drop model, where you have a simple ansatz in terms of the number of nucleons. So I will start next week by discussing this example here, and then we're going to dive a little bit deeper into the mathematics of linear regression. But I'm going to give you as a kind of homework, take a look at the slides from today, these introductory slides. Try to install the different Python libraries which we are going to need, and start taking a look at this data set here. So that's where I'm going to stop today, and I'm going to stop the recording here.